Welcome back everyone to this lecture on multi-class activation functions. So previously we just saw that all the activation functions in the previous lecture, they make sense for something of a single output. Either you're trying to predict a continuous label or you're trying to predict something with a binary classification problem. That means you either want a 0 or a 1 or something between 0 and 1 and assign it a probability. But what do we do if we actually have a multi-class situation? In a multi-class situation, the output layer is actually going to have multiple neurons. So keep in mind there's two main types of multi-class situations. There's the non-exclusive class situation, and non-exclusive basically means that a single data point can actually have multiple classes or categories assigned to it. A mutually exclusive class situation, which typically when you're learning about machine learning is the more common type, is where you can only have one class per data point. So let's go ahead and look at the activation functions for these two use cases. So first off, for things like non-exclusive classes. Again, that's where a data point can have multiple classes or categories assigned to it. So for example, let's imagine your data happens to be a photo. A photo can have multiple tags. It can be tagged beach, family, vacation, etc. So it can have multiple classes or categories then assigned to a single photo. For a mutually exclusive class, that data point can only have one class or category assigned to it. So for example, photos can be categorized as being in grayscale, black and white, or full color. A photo can't really be both at the same time. It's either in grayscale, black and white, or full color. You can't assign both of those classes to a single data point. That wouldn't make sense. So that's mutually exclusive. So what we want to do is first figure out how do we actually organize data that contains multiple classes. And the easiest way to organize multiple classes is to simply have one output node per class. So previously, if we look back at that neural network that we were drawing out and illustrating, we thought of that last output layer as a single node. That single node could maybe output a continuous regression value or a binary classification, 0 or 1, or maybe some value between 0 or 1. However, let's now expand this output layer to work for the case of multi-classification. So what this ends up looking like is we have our input layer at the very beginning, then we have some hidden layers, and then we have a final output layer, where the final output layer is essentially a neuron per class. So that there's one neuron for class 1, another neuron for class 2, all the way till n classes. So this means we need to organize categories for this output layer. We're not going to be able to feed a neural network categories like a string red, blue, or green. Recall that the neural network is going to take in X values, and those should be numbers. Then it can apply weights to them and add biases. You can't really multiply the words red, blue, or green. And often, real data points, when we have classes, they're going to be things like string codes. So we have to figure out how do we actually transform our data correctly to be able to use neural networks for multi-class situations. So what we can do is we can instead use something known as one-hot encoding. You may have also heard this called dummy variables. So let's take a look at what this looks like for mutually exclusive classes. So for mutually exclusive classes, you may have something that looks like this. You have data points and then a class that belongs to each data point. Here we can see data point 1 is red, then 2 is green, 3 is blue, all the way until data point n is red. Now we're not going to be able to feed these string color codes, red, green, and blue, into our neural network. So how do we actually organize this, especially considering that last output layer? What we can do is actually just use binary classification for each class. And what we do is we end up building out a matrix. So you can see here, we say data point 1 is 1 for red, and then 0 for the rest of those classes. Then data point 2 is 0 for red, 1 on green, and 0 for blue. And you can see how we can essentially expand this idea. So again, this is called one-hot encoding, and other people like to call this creating dummy variables. Now for non-exclusive classes, it's going to be slightly different. Recall that non-exclusive classes means each data point can actually have multiple classes assigned to it, such as a photo having multiple tags or categories assigned to it. So we can see here data point 1 has classes A and B assigned to it. Data point 2 is A, data point 3 has C and B, etc. So we just actually performed the same idea, except now data points can have a value of 1 for multiple categories. So same idea here, you're essentially where that data point matches up with a class or category, you assign it a value of 1, everywhere else you assign it a value of 0. Essentially transforming or encoding that string information as one hot. essentially showing that 1 means on and 0 is off. So now that we have data correctly organized, and we're going to be organizing data and one-hot encoding our data later when we're actually coding, all we need to do is choose the correct classification activation function that the last output layer should have. So if you're dealing with non-exclusive, then you can just use the sigmoid function because each neuron will output a value between 0 and 1, indicating the probability of having that class assigned to it. So what this looks like is we again have a neuron for each class. Again, this is non-exclusive, so data points can have multiple classes assigned to them. Then you just end up putting a sigmoid function. Recall a sigmoid function, also known as the logistic function. It can go have values between 0 and 1, and then all the outputs for those neurons end up lighting up somewhere between 0 and 1. And what you end up doing is you just say, okay, in this particular case, this data point has an 80% likelihood of belonging to class 1, as well as having a 20% likelihood of having class 2 assigned to it, and then maybe a 30% likelihood of having class n. So we would probably just say, all right, go ahead and assign class 1 to this data point. However, keep in mind that when we're dealing with non-exclusive classes, you can see here that, let's say I ran another data point, and I happen to say class 1 is, after going through a sigmoid function, 0.8, class 2 was 0.6. For the non-exclusive case, if my cutoff point is at 0.5, then I would actually assign here two classes or two categories to this data point. I would say both class 1 and class 2 are going to be assigned to this data point since I'm dealing with non-exclusive classes. Again, the classes aren't exclusive, so data points can be assigned multiple categories or multiple classes. So in this case, since class 1 and 2 kind of breached that halfway cross at 0.5, we assign both 1 and 2 to this particular data point. So as I just mentioned, for non-exclusive classes where we're using that sigmoid function, always keep in mind that that allows each neuron to output independently of the other classes. So it allows for a single data point fed into the function to have multiple classes assigned to it. Now what do we do when each data point can actually only have one single class assigned to it? Well, for this, there's a really clever softmax activation function. So the softmax function looks something like this, and essentially what you end up doing is recall here that we have z as the actual inputs into the last output layer, and what we're going to be able to do is with this particular softmax function, notice that it actually has I is equal to 1, then 2, all the way to k, and k here stands for the number of categories. And essentially what this does is the softmax function calculates the probabilities distribution of the event over k different events. And in this case, k is just the different classes we have. So this function will calculate the probabilities of each target class over all possible target classes. So the range will be 0 to 1, and what's really important here is when you're using the softmax activation function, the sum of all the probabilities will be equal to 1. So that means in that output layer, when you're passing in through the softmax function, the sum of all the probabilities in that output layer is equal to 1. So what you end up doing is, since the model returns the probabilities of each class, the target class is chosen by the neuron that has the highest probability. So what does this actually look like? Well, the main thing to keep in mind is, again, we're dealing with mutually exclusive classes. So for that sort of problem, after you apply the softmax, you get an output that looks something like this. You have some index position that matches up with those neurons in the output layer, and then softmax provides probabilities for each class. So we can see here for this particular data point, we had 0.1 for red, 0.6 for green, and 0.3 for blue. You'll notice that the sum of all those probabilities is equal to 1, which makes sense because the sum over an entire probability space should be equal to 1, because that basically answers the question that there's a 100% chance this data point belongs to one of these classes. But if we read into this further, this basically says there's a 10% chance it belongs to red, a 60% chance it belongs to green, and a 30% chance it belongs to blue. So for this particular case, we would choose green as our classification for this mutually exclusive class and say that this network believes that this particular data point is green, and it gives it a 60% chance of being green. And as I noted, the probabilities for each class all sum up to 1. We choose the highest probability as our assignment. So, for a review of the theory we've gone over so far, we understand basic perceptrons, how they can expand to a neural network model. We understand weights and biases and how those get passed in with an activation function, and we also learned about particular activation functions for multi-class situations. However, we haven't really discussed how the network actually learns. How do we update these weights and biases in order to improve our performance? Initially, they all start off just random weights and random bias values. Eventually, we're going to have to figure out how this network is actually going to learn to choose correct weights. And for that, we need to first learn about cost functions, and then we can learn about things like gradient descent and backpropagation. So let's go ahead and go over cost functions in the next lecture. I'll see you there.